Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today I should not say it's joint work. A more proper thing to say is ongoing work. So here, unlike the previous two talks, the first talk was about a history about support vector machines. The second talk was a nice research result about training large-scale linear SVMs. So this is more about struggling with this question which I have. So there are many good PhD students here. This is a good problem for a PhD. So please ignore if you don't like the solutions which I'm going to present are not very elegant. I'll point that out. But it's more to see if the questions are interesting or not. So it started in 6-7 years ago in the campus talking to some biologists. So they said that automatic classification of protein structures is something which you need solutions. So the idea is that you're given a protein structure. As a protein structure for us, it's nothing but a collection of coordinates in 3D. To be more precise, there are certain things. There is a backbone which is sometimes called the C alpha atoms, right? They are in a very quickly fashion, in 3D space sets, and you can find out their coordinates. So protein structure is a set of such coordinates. Now they often have labels like this belongs to this family or belongs to this subfamily, etc. Now an automated tool would do the following: take this structure and assign a label to it. We standard classification problem, if you like. Now the few thing remains is right. So 12-13 years ago, Professor Kirti taught me support vector machines, and he convinced me that for any classification problem, that's the thing to do. So we said, okay, we'll learn to work with SVMs, and this idea has been resonated elsewhere also in the world. So the key problem here is, how do you represent this set of coordinates? So in the previous two talks, there was this excessive focus on feature vectors, right? What's a feature vector for protein structures? I talked to biologists and said that no, we have never heard of such things. So I said, how do you do this? Then said that, okay, existing methods often do the following: take two protein structures, superpose one over the other, which is sometimes called the alignment process. That will tell you how similar these proteins are. Use that in a way to take your decisions or find your labels. Okay, so this becomes an interesting issue that, okay, take two structures, you find this alignment, there are some alignment tools, and from that you drive a kernel out of it. So this is also by no means a solved problem. I mean, there have been attempts. We have done something, others have also done something. So this goes on. So we have some results now. So you see, you take these two proteins. This is sometimes called a cartoon of a protein, and and they align them. That is like you superpose one over the other and try to measure how similar they are. So root mean square deviation is a measure of that, and then try to compute a kernel function over this. Remember, I'm not talking about. I'm sorry, I should have given some definitions of kernel functions. I was thinking the previous speakers would do that. So since they have not done it, so we'll skip it. So the thing is, kernel functions require certain mathematical properties. But in essence, you can say the kernel function takes in two data points, which could be protein structures, which could be two vectors, and try to compute a notion of similarity, if you will. So that means alignment is a very good idea, but you have to do something more to satisfy these properties. So we had this tool, and then so we did this work, I see 2007, ICML and all that. So then we thought we'll build a big, really big scale structure classification tool setup. All right. So went to our grant agency. So they looked at my result and said, fine. But you see, the hardest problem is, where do you get your coordinates? Apparently, these coordinates are obtained from X-ray crystallography. And the biggest problem what they find is that these numbers are often unreliable. That means the coordinate values I am getting is unreliable. So what do you do about this? So that started off this thing. So for example, so here is, as I've shown you this previous, and now often if you go to protein data bank where people upload this coordinate information, you will see they will often upload another number which is sometimes called the resolution information. So basically each coordinate is guaranteed to be within this error bar, 1.8 angstrom. Angstrom is a unit, right? So far in the literature we could not find anybody saying anything about this. So we wanted to check out, so can I ignore this? Can I ignore this uncertainty? Fine, uncertainty is there, ignore it, things will be fine. Apparently, what we find is, in this, the root mean squared deviation, that means when you superimpose one over the other, that is at 3.9 angstrom, whereas the error bars themselves are something like 1.8 angstrom and 2 angstrom. So clearly this is very unreliable. If it is randomly part of the structure, randomly. Obviously the kernel values also, are so I can't be sure about this kernel value. It could be anything between these two numbers. Now, so this, now one might say that okay, these numbers look, it doesn't look to be too big, but unfortunately, for this family which you have taken, let us say, 60% of the proteins lie in this range. So that means if I randomly perturb the structure a little bit, my kernel values look very different. So I can't ignore it anymore. So this raises this question. Yes?
The thing that people do in vision is they will vector quantize. You could just break your space up into grids and then you say there is uncertainty, but I know it's more or less in this grid. And that buys you a little bit of invariance, which at least in vision is proved helpful. And would a trick like that work here?
So in your vision, often you treat a data point as a vector, right?
Yeah, but where the interest point fired or something, there might be some ambiguity about that. So you just block that. You tie your image into quadrants or whatever.
Right.
And then you say it just occurred in that particular cell in the grid.
I'll come back to your question in 2 slides.
I had a question.
Sure.
When you say random perturbation, are you talking about local perturbation or global?
Global. You can also do local if you like, because each coordinate is just guaranteed to between the error bar, right?
But these numbers are for
Global.
Just rotation.
And if you do local, it will be even worse.
So is it just rotation and skew, that kind of a thing, or is what kind of?
No, what you can do, see, from protein data bank, all you get is the center coordinate numbers, right?
Yeah.
And it is saying that 1.8 angstrom. The nearest atom is 1.8 angstrom.
Yeah.
So you just take, whatever perturbation you like. So in a sense, see, I couldn't get any clear answer like what is a good rotation, what is the thing to do, So here we said, okay, let's randomly rotate it, or rather randomly perturb it and see what happens. And the answer I find is that okay, my k is uncertain and this and that, right? So what do you do? So that's the question we are going to ask today.
Sorry.
Yes, please.
You have this 1.8 angstrom. What does it refer to with respect to which structure?
So this is respect to this structure.
But what it means with respect to?
So now this basically means that the distance between the two coordinates is with error bar of 1.8 angstrom, right? Yeah. Sure.
If you did some type of MDS simulation on something like this, like with a rough version of the structure, could you refine the uncertainty of the kernel values a little bit more, or is that too much computation to do?
As I said, is a good suggestion. I have no idea, but could be. So, see, this is a more like questions, So maybe that's a good idea. I don't know. So good, don't know. So the idea is that, as I said, today we want to use SVMs. Why? Because Professor Kirti has convinced me that's the thing to go. So now if you can tie that thing to SVMs, it should be fine, I guess. Okay. So obviously, here is sort of thing, right? Now in Vijay's slides you saw this equation, so I don't have to tell you anymore this equation. Now the thing is, these numbers are uncertain. I don't know. It's not that I don't know completely. I know something. They lie in a range. So that leads to this question: Like what? Sorry. Like what if k is uncertain? So that's the question we have. Okay. So this builds the agenda of the talk. So basically we're going to look at this problem motivated from protein structures, and now you must say, okay, it appears in protein structures, computational biology. Computational biology is a great subject, but I don't care. The same problem occurs in other places also. For example, if some of the values are missing data, right? The kernel entries would again be uncertain. So it's not a problem which is related to only computational biology or some niche areas. It happens in many places. So that led to this fundamental question, like what do I do? So I'm struggling over the last few years. So today we'll talk about some, okay, we already talked about problem definition to some extent. So I'm going to propose what we have done so far. So there are two ways I find literature of treating this problem. One way is you have a probabilistic model of uncertainty. So that gives rise to a certain type of optimization problem which is sometimes called chance constraint program. So this has been published in ICML 2010. Solutions are there, but a lot more needs to be done. The other view is you represent uncertainty in sort of a geometric way. And this is often studied in the area of robust optimization. So those of you, if you haven't heard about it, I want to know more about it, you should attend Konstantin's talk. He also has a very nice paper on how robust optimization is used in machine learning, for the matter. So that makes my life very easy. Any questions of kernel methods or SVMs will go to Kirti. Any questions related to robust optimization should go to Konstantin. Okay. Whatever. And so what we find is this robust optimization setup. We'll show you some result. And an interesting result is that purely from an optimization perspective, we could design a new algorithm for a special kind of saddle point problem, which has something like O of 1 by t square convergence. So this should be the optimization issue. And if I get time, we'll talk about how do you predict and and what are the error measures, or rather, how do you measure robustness, etc. So that should be the agenda of the talk. Okay. Now coming back to this. So this is the basic question, right? There's an SVM classifiers with uncertain kernels. So why is it hard? Now, please try to visualize in your mind, how will I compute the kernel? I do an alignment process, which is essentially something like a dynamic programming. And then to compute a kernel, I mean, you do many other things. For example, there's the spectral method and etc. So finally, there's no closed form formula for us. That the kernel, it's a k of x comma y, right? It's like the Gaussian kernel. You have a formula for it. You can play with it. I don't have a formula, I have a program which takes into protein structures will give me a kernel. Right? So this is what I wanted to show with now for an image perspective, right? I don't have a simple formula that from the coordinate, if I perturb this, kernel value is going to change this. There's no simple formula for it. Rather, a computer code will give me that value. Okay, so
we can take this offline.
Yeah, sure.
What I'm saying is you can buy invariants to spatial perturbations by vector quantization.
Sure, so we can look at that. Maybe offline is a better thing. Right? So basically, so you're not allowed a closed form formula for the kernel. That means you cannot say, okay, if you perturb the coordinates a little bit, my kernel value is going to change a little bit because of this formula. Such things are not available. You're only allowed to treat it as like a black box. Secondly, somebody raised the question that what about uncertainty in the what kind of uncertainty it is? We have no clue. So a detailed model of uncertainty is not available. Yes.
So only access to labeled training data points is allowed, or you can access some unlabeled?
Yeah, both are there. Both are there. See, the thing is, the protein structure has a label, family and all that, right? Now, a structure consists of what? A set of coordinates. Now, asking the coordinate values are given to you, that itself is noisy. That's the question they asked me at the grant agency, and I got stumped. And still I'm stumped. So it gives rise to a fundamental problem, at least in my sense, in whatever I understand, in SVM literature, that if the kernel matrix is uncertain, what am I going to do? And this is not related to only computational biology. It appears in other places also.
But what I asked was that you have access to, so you are saying that you have black box access to kernels. So what I'm asking is that given a point, can I compute kernel value to any labeled training point only or any unlabeled training point also?
You can create any unlabeled training point also. But okay, I think what you're trying to ask is that do you have a even one clean protein structure? No. All protein structure you take will have a problem with the resolution. Correct? Okay. So basically, you can assume some minimal information about that. Like as I said, right? The kernel values lies in a range, or you can even assume there are some mean variance, that second order moments, that kind of things are available. You can draw samples if you like, but I can't give you this distribution or it lies in this set, nothing like that. Okay? So obviously there are two issues. First issue is how do you train with this, right? How will I train? How will I build my classifier? The second issue is how do you measure robustness? So today's talk, keeping in the theme of this spirit of this today's talk, it will be more in this issue about how do you optimize about these things, right? So literature survey, first thing. Let's see what people have done. So a different version of the problem where you have access to a feature vector. You're going to ask the same question. What if these xi's are noisy? Right? So this has some literature. It started off with Laura's work, who's really one of the pioneers in robust optimization. So he studied this problem that each feature in a vector lies in a range. And he gave a nice L1 type solution for this. We ourselves studied a different problem where we're studying missing values problem. So where we assume we say that okay, xi's are noisy, we have access to his mean and the covariance information. So later on we find that this is good, but it's too demanding. I mean, nobody will give you a full covariance matrix.
So what is the I there?
Ith data point.
Ith data point.
So your
vector.
Yeah, xi is a vector. So mu I is a mean vector. So I'm saying the ith data point is noisy. So an example is a missing values. So you can fill it in, but actually it's a random vector.
So each example is being represented by us.
Yes. So that's one way of treating this. I mean, there's also there in Duda Hart in one of the sections, but he doesn't expose it in detail. So that led to more work, what we also did, and saying that okay, very rough information. For example, just have bounds on the moments, etc. So okay, that's a different story. So these are mostly for problems where I have access to feature vectors, right? So none of them will apply to our scenario. At least we don't know how to immediately apply these techniques in an obvious manner. So bottom line, I couldn't find any existing work on uncertain kernel matrices. Any help would be very welcome. If you know any literature, please point me to this. So then as I said, that there are two ways of looking at it. One is you build a probabilistic model, another is you build a geometric model. So let's talk about the probabilistic model first. So I make the assumption that this K matrix is uncertain is a certain matrix, certain kernel matrix plus a random matrix then. Right? So you remember? So you go back a few slides. See this second compute, right? So this is like a K bar. Right? I take the average. So yeah. So I say this uncertain matrix K bar, K is equal to a certain matrix K bar plus Z, where Z is a random matrix. Yes, please.
Are you assuming that K is still positive or positive?
Good. Yes, very good. So you see, there are lots of things we will talk about. That's a good point. Very important point, right? So basically, if you write SVM dual, all this funny half alpha I, alpha j, all that can be written in a matrix form, like this. I have introduced a new variable t. there, but it's easy to see that this is the same problem you're talking about here. Now here, this k is uncertain. That's what you're talking about. And this I've written on the standard SVM classifier, and this is my b term, you know, and all that. And this is my classifier, right? This is a standard problem, and here the k is uncertain, and we say that we model uncertainty in the form of k equal to k bar plus z, right? That's the way. So what do we do? So there is this chance constraint setup which says, okay, since z is random, right? I do not know what value it will take, right? It can take. So one way to do this is that if you consider this as an event, but this is a random vector, random matrix, right? This randomness is coming from this, right? So we say that, can you ensure this event holds with high probability? This is like a constraint, but see, this is a different kind of constraint. It's a constraint on the probability of an event. This is something called chance constraints, right? Yes.
What constraint holds? Can you just read that out?
Yeah. So probability of this event. The event is that, I don't know, you can see this, that alpha is less than t. Okay. So in the SVM dual, right, you have this quadratic term, no, where the k appears. So write it, put that in a constraint, introduce a new variable t in the objective. So the linear term minus half t, I call it, and I write all the other terms less than t. Correct? So I get the k matrix in the constraints, right? Now here alpha t are all. I'm sorry. So here alpha t. Oh, sorry. Here alpha and t are all deterministic variables. These are decision variables, right? Alpha and t are decision variables, right? The randomness is coming through z. So now I'm trying to say now, okay, how will I treat this? Let me do this. Let me say the probability of this event happening should be very high. There's a constraint I impose where this epsilon is a user-defined parameter. Epsilon is like 0.1, if you like. This event happens with high probability. That will do my job roughly. Right? This is called chance constraint setup. Yes.
But you haven't told me the distribution.
Yes. See, that's the challenge. That's the challenge. No. So that's the challenge. I don't know the distribution. So how do I go about doing it, right? So now, if you want to write it a little bit more fancy way, you can say write it a trace of multiplication of two matrices, where A is this matrix. And now, coming to Fisher's question, yes, k bar plus z must be positive definite. How do you solve this problem? Well, yes.
The formulation is still not clear to me.
Sure.
Going back to Pratik's question.
Yes.
Even if you could solve the problem for training, at prediction you would still have uncertainty.
Yes.
You just solve the problem for training.
Yes.
The important thing is prediction.
Yes. Let me see if we get time. We'll discuss this. Yes, of course. There are many questions arises. That's why I said there are two aspects to it. And how do you predict, and what error measures? How do you measure robustness? Yes, pretty much. But for the time being, let's assume that, for the sake of discussion, let's assume that we are interested only in the first question. That is, let's say there is error only in the training set. Okay? Yes.
So, is there a relation, if I were to try to do this, think about the SVM as some type of likelihood, right? And then I put some type of distribution on K, like a Wishart type of distribution. And then if I look at some type of posterior, and I looked at credible, I would put that back in the probabilistic coefficients.
See, the thing is, you do not want to get away from this nice setup, the QP setup, right? That's one reason. But your point is valid, that can I like good and all that. But what we have found in our analysis is this optimization problem will change. You don't be in this form anymore.
Yeah, sure.
So which has other advantages, right?
Okay.
So that's the thing, right? So this is the thing, but.
In answer to that question, PP likes SVMs are not Gaussian processes.
So that is between you two. Right. So what do you do? The answer to this question is, I am not smart, so I relax the problem. So what I do is, so these are things you should keep in mind. So I drop this PSD constraint for the moment. I drop it. So obviously it's a bad thing to do. But I don't know anything better. Maybe you have something better ideas, here you can do something here. So next thing, even then I couldn't solve this problem. I went and made this another atrocious assumption. The z's are independent. It's laughable, right? But I don't do anything better, I'm saying. I don't do anything better. So of course, okay, just to make sure that at least they're symmetric, that much you can assume, but they're independent. Right? So we could solve this problem to some extent, giving all these nasty, dirty assumptions you're making, where z's are Gaussian and another is lies in an interval. This comes close to the protein structure thing. Now, here we find, how am I doing in time? Oh, good. Okay. So if I assume all this and z's is Gaussian, then I can use this result. It's very easy to derive that for any matrix W, if z's are Gaussian, right? The probability of this event is exactly this, where phi is a standard Gaussian. Yes, please. Yes.
So let's say like the features, the uncertain kernels are coming from uncertainty in feature vector itself, right? In some sense. So let me take a concrete example. Let's say you're using these Gaussian kernels, right? And the uncertainty is coming from feature vector themselves. Then effectively instead of additive component, you actually have a multiplicative component, right?
Now, if the uncertainty is in the feature vector, we already have some solutions which are shown in other slides. So here for protein structures, there's no feature vector. If you say feature vector and at least the biologists there, they just walk off. This is ridiculous. So they'll say that anything you have to do, you have to find alignment first, which is basically comparing to proteins, right? Don't give me a bunch of numbers which can describe proteins. That's what they have. Okay. And the other thing is that if you have access to, as I said, access to feature vectors, I have other truths. I don't have to do all this. I showed you some of these things. I mean, right? Okay. So now if you do this, say then using this relationship, you can relax the problem to you can write a equivalent deterministic problem, which is this is equivalent to this deterministic problem. Yeah, that's very easy to see. So I took this problem. If they're independent and symmetric, all that, Gaussian, this and that, then I can write the SVM problem with noisy kernel as something like this, a deterministic problem. But it may not be easy to solve. That's another question. Right? So here remember, see, we want it less than t, right? That's 1 minus epsilon. So this is the complementary event. So this probability should be low. So epsilon is something like 0.1. So this phi inverse of epsilon would be a negative number. Sort of. And then, okay, so then he said, okay, this is Gaussian is, can you do better than Gaussian at least? I mean, we already made some atrocious assumptions. Okay, so there also things are not that easy. At least we had to invent a new bound, sort of, which is of similar nature. Right, this is bound is motivated by more by a Bernstein type inequality. So finally, both for Gaussian or this finite support, we like to call it, where each z's between this is given by a constraint like this, where this kappa is a constant. For Gaussian, it is minus phi inverse of epsilon. So epsilon is a very small number, mind you. So phi inverse epsilon is a negative number, so kappa is positive. Right? And for finite support SVM, you get a similar thing, but the constant just changes. And of course, this beta ij definitions also change. Now, since this is a spirit of optimization, let's see how we'll solve them. So,
Is this convex?
no, not in general. So, okay, this is good. So we will talk about this. So beta is rank 1. So beta is also a matrix, right? If beta is rank 1, then you can show that it is like an SVM problem. Okay, now if beta were PSD, if beta were a PSD matrix, again you can relax it to a convex program. In particular, relax it to a second order cone program. If you feel little, how do you say, haven't heard this second order cone program, we can talk about it offline, right? So these constraints are sometimes called second order cone constraints. But for general beta, this is a non-convex problem. In fact, this is an instance of a co-positive program. So so what we do, again, you do a local search, modified quasi-Newton, etc., dirty method, right? So this is our state of the art so far as probabilistic model of uncertainty goes. Clearly, it is very, very bad, I would say. More needs to be done. So then, keeping all this in mind, so what are the shortcomings? Independence assumption, I've happily dropped this, so this might lead to not valid kernels. This is a primary objection to this, right? And optimization turns out to be non-convex in the general case. Secondly, even if the most likely case in our experiment, what we find is beta turns out to be mostly PSD. I mean, that's experimental observation. Even in such a case, solving the large scale thing is even out of bounds because you are using second order cone program, etc. Right? So how do you address this? So this is the part where we're coming to the joint and the ongoing work. So now we are looking at robust optimization. So the RO setup considers problem of this kind. So you have a function to minimize in a variables x, and you have m constraints, right, which are functions gi of x, and theta is a parameter. Think about it, a linear program, C transpose x, x greater than or equal to b. Now your a is uncertain or something like that. That's the problem I'm trying to talk about. So here it says, so if I ignore this is nothing but a standard nonlinear program. If f and g are convex, this is a convex program, etc. What are techniques there to solve? But the problem is if theta is uncertain, and say for example you say theta lies in a set U. I'm saying theta is uncertain, but I know something. That means theta lies in a set U. Then I have to make sure this. For every choice of theta, this needs to be feasible. For every set of theta in this set U, this is feasible, right? Now if the set U is like a sphere or something like that, right? Then this will generate for you infinite set of constraints, right? This is an instance of semi-infinite program. Obviously, finite number of constraints, finite number of variables is problem enough. So semi-infinite and all that, this problem is not easy. I mean, so obviously people have found that tractability depends on U. Mostly it's hopeless, but sometimes because of set U, this might be useful. So there's a very nice book by Professor Benthal where he introduces this. And now people are interestingly finding, this is beginning work where people are finding that such kind of paradigms may be useful in machine learning. So Constantine has a very nice paper one should look at. Okay, so we want to borrow this setup for our problem. That's the thing we are talking about. Now Professor Benthal in his book gives many examples where he shows that to make these problems tractable, often you should take a geometric view and try to come up with an affine model of uncertainty. That means theta is equal to some linear combination of some other known thetas, something like that. That sometimes leads to a very tractable problem. So we wanted to explore that. So as we see here, this is a constraint we have, right, from our SVM problem. Now we are now saying this uncertainty k lies in a set. This k lies in a set U. That's a only change we have. Previously we had a probability. Now you're saying this k is again uncertain but lies in a set U, right? My decision variables are still alpha and t. So we choose k, this capital set k. Sorry, this set U, the uncertainty set U, as an affine set, wherein we say that I have given this k bar, of course, plus some, say, capital L number of known matrices, which can be computed by simulation, for example, right? So my uncertainty set is the existing kernel is k bar plus a positive constant into kl, where the kls can be computed, by simulation, etc. Now, first of all, let's check the following. If eta l's are positive, right, and this is a valid kernel, and these kls are valid kernel matrices, then this is a valid kernel matrix. So so I've addressed one of the issues. Okay, so I've talked about a problem now. At least I'm talking about things which are valid kernels, right? So now the next thing, how do I go about doing, at least building a classifier for this purpose? Now, so as I said, this leads to infinite number of constraints, right? So one way to satisfy that is you try for each x, if I can show the maximum value of this for a fixed x, right? Maximum over the theta. That is less than 0. That is equivalent to satisfying this condition. Correct? So that's one of the things. So then, when you do that, that problem turns out to be exactly equivalent to this problem, where you say max alpha, but that remains as is, but you minimize over all choices of k in the set uk, and you have this standard SVM objective function. Now that is very easy to see from that. Right? Now, yeah, so that's probably the main thing. Now, once we have a problem like this, so you see this is a max-min problem, right? Now the next question is how will I solve this, etc. So first of all, to make progress in trying to solving them is you rewrite the problem in terms of these variables, eta, right? Instead of this uk. Now you observe the following, that eta is a linear function. It appears linearly in this, right? And it lies in a ball, for that matter, right? And alpha is as you see. So for a fixed eta, all of them is like a SVM, sort of, with a different kernel. These are the observations we have for the moment. Now the next attempt, what we'll try to do is try to give an algorithmically how we'll solve this. Now again, this problem, especially for, so I should mention one thing. Here I have not described the ball properly for you. So this is the LP norm. So for a discussion, let's take this as 2. So it's like a ball. But in such a case, you can write a very nice second order cone program for this. So this is a finite problem, you see. And when you solve this, you could probably get an effective kernel of this kind. Right? So from this solving this problem, we will get these alphas, right? See your question that what happens on certain data point, that's still to be answered. But the training point will give me some alphas. So that's the point we have at the moment. Okay. Now the question is, so the first question we asked is, can you do better than this second order cone program? It turns out that yes, you could do even better, that you don't have to use the second order cone program solvers. So if you revisit the problem again, this is the original problem we had, right? This is a max-min problem, and if you look at this function, h. Now, as we commented before, this h has these two properties, that is linear in eta, and this lies in a convex set. If p is 2, it lies in a ball, like in a positive quadrant of a ball, and this function is very nice. All derivatives exist, etc. Now, it appears that this can be solved by a recently developed algorithm by Nemirovsky and Juditsky. So, but we can write. They propose a very general algorithm. But we can write to my mind, this algorithm is still complex, but we can write a much more simplified proof for this setup here. Okay, so let's revisit their algorithm. What they say is, suppose you have a saddle point algorithm, right? Min-max phi of x comma v, where variables are x and v. Okay, so think about the set. So the domain of x is this, and domain of v is this. So this is your total domain. So phi is a function from z to r, sort of. You require phi to be differentiable, all that. But the key thing is, phis of the form is linear in x. That's the key. Linear in x, and you have AV plus GV are functions of v. And now these, but they can't be any functions. They should be nice concave functions, which is strongly concave for the math. See, to note the maximization over the v variable. So I need this a and g to be concave functions. Okay, so this setup they have. In that setup, they proposed. So we are going to put it in a way so that it directly applies to our case. So their proposal is based on the notion of prox functions. So which maybe I don't know whether that related to Gilbert's algorithm. Maybe it will come down to that. So to define the prox function, so people know breakband projection, we're talking about the same thing. So the way to go about doing this prox function is you need a notion of a distance generating function. So for example, if you take this function, half z squared, now you try to evaluate this where omega dash is a derivative. See, you will get this, right? This is like a distance, right? So another example is if you take the negative entropy, that is like zi lies in a probability simplex, right? And if you take this, you apply this formula again, you get this Kullback-Leibler divergence. So such omega z's are called distance generating functions. Why? It generates a distance. So distance like. So for example, this is not a distance, right? Distance like functions, right? So we call such omega to a distance generating function. Now we need one more notion. The notion of a prox function. So prox means proximality, right? So take a variable. So the prox function is defined as that you minimize over a set this expression. Now this expression ensures that given an arbitrary point z, find a point z rather, in this set which is closest to z, closest given by the distance generated by this omega z. Okay? Yeah. So how much time I have? Oh, so really sorry. Okay. So main result. So I'm sorry. So the algorithm goes like this. So the algorithm goes in various sort of stages. So remember, the v variable is our alpha variable, right? So that's a problematic term. So it ensures, so it assumes that you know this, the starting point is R0 close to the optimal solution. You just know this. Now that can be very bad also, a very bad bound. So in each stage, what you do is you just do, so I will say this is like projection of z, right? Projection of xi variables on this set. So what you do is you take the gradient and project it. So this g is nothing but the gradient of z, that is that x and v, and you do it multiple times. So in each step there is a step size which I can compute exactly. There's a formula for this. Now you do it in each stage. You do this. So you take this gradient projection steps, and if you do finite number of such steps, you reach optimality. Now the thing is, here in each step you have to make sure that the distance generating function has something to do with this your stage, with the VS, right? I'm sorry I don't have time. So but the final result is, if I do enough steps, I can show that I can get a solution which is epsilon close to the optimal saddle point in ms squared steps, O of 1 by m squared. Pretty fast. Gradient projections. What is the computation? The computation would be something like this. You remember the v is like the alphas, right? So they will just equivalent to projecting on an SVM, right? And your etas have a closed form expression for this. So that's very fast. So since I don't have time, I will just flash one slide. So I don't know, yeah, to show you that this is our training time comparison. So these bold lines are your second order cone program based solvers, and this is our our saddle point based solution. This is just saying the scale, but again I'm hopelessly out of time. I didn't talk about the main problem of predicting the uncertain things, but I will happy to talk about offline. So maybe I'll stop here. Yes, Vijay.
Short of time, but a quick question.
Yes, Vijay. Sure.
In the way you are formulating the robust kernel, the kernel with the uncertainty,
right,
more or less seems exactly like what you do in multiple kernel learning.
Yes, so, but the difference will come is when you want to predict. So optimal problem is very similar to multiple kernel learning.
So that's why it's not very surprising that optimization.
Yes. So it's a very good point. For example, the saddle point algorithm we wrote down can also be written for multiple kernel learning.
Yeah.
Right? So it's a good observation. But the thing is, okay, we were talking about this uncertainty business, right? That's but anyway, we don't have time.